Hello everybody, and welcome to our video on the product and quotient rules for derivatives. So we're going to start here with the product rule. This says that if both f and g are differentiable, then f times g is differentiable, and its derivative is given by the derivative of f times g with respect to x equals the derivative of f with respect to x times g plus f times the derivative of g with respect to x. Or equivalently, f times g prime equals f prime times g plus f times g prime. Okay, so we're going to go ahead and look through the proof of this. This proof has a little bit of a clever trick in it. Most of the proof is pretty straightforward, except for the clever trick. So we really got to make sure we just see what's going on there. So first, I'm just writing out the derivative with the definition. The limit as h goes to 0. Since we're looking at the product function, it's f of x plus h times g of x plus h minus f of x times g of x all over h. Now, what we're going to do here is, in order to rewrite this in a way that'll let us split this up into some usable separate derivatives, we're going to cleverly add 0 in between. So in the middle of our numerator, what we've done here is just added 0. We took negative f of x times g of x plus h plus f of x times g of x plus h. That's really 0. But the reason we've done that is because now, when I add that up like that, I can separate this into two different fractions. The first two terms, f of x plus h times g of x plus h, minus f of x times g of x plus h, all over h, plus the second two terms here, over h, f of x times g of x plus h, minus f of x times g of x. And what did that do for me? This clever subtraction and addition of terms gave me a shared term, or a shared factor, in each of my pairs of expressions. This first pair of expression shares g of x plus h. The second expression shares f of x. And now that means I can factor that pair of terms from each of those. And so that's what we'll see momentarily. So the first thing we're going to do, split the limit into 2. We can always split limits on sums if those limits are convergent, which we will see that they are. And so we split the limit into 2. And here on the left-hand side, we factor g of x plus h out. And on the right-hand side, we factor f of x out. And so now we can split the limit up on products. So remember, limits can be just split up on products. That's not the case for derivatives, which is what we're proving now. But we split up each of these individual limits, g of x plus h times the limit of f of x plus h minus f of x over h, plus the limit as h goes to 0 of f of x times the limit as h goes to 0 of g of x plus h minus g of x over h. And so here, g of x plus h, if h goes to 0, I just get g of x. This is the definition of the derivative of f with respect to x. F of x is not a function of h here, so this is treated as a constant. So the limit of the constant is just that constant, f of x. And finally, this is the definition of the derivative of g with respect to x. Okay, so that's our proof for the product rule. So again, f times g prime equals f prime times g plus f times g prime. We're going to use this rule a whole lot. And we're also going to use this rule, the quotient rule. So if both f and g are differentiable and g of x is not equal to 0, then f divided by g is differentiable and its derivative is given by the derivative of f over g with respect to x is g times df dx minus f times dg dx over g squared. Or equivalently, f over g prime equals g times f prime minus f times g prime over g squared. So I've heard many different little catchy phrases to help memorize the quotient rule. So I'll just put one of those down here in case it helps. So I've often seen low d high minus high d low over low squared. So sometimes people find that has a nice little rhythm or musicality to it that helps them remember it. Low d high minus high d low over low squared. If that helps, great. If not, just you can memorize the formula outright. But we definitely want to make sure that we know this formula when we're dealing with any sort of quotient functions. So with that being said, let's go ahead and look at a proof for this. And the nice thing about the quotient formula is that we can actually prove it fairly easily. I see there's a little odd comma here. I'll add a little space for that comma. Maybe we'll just... There we go. That's a little bit better. Sorry, just adjusting formatting here. Sorry about that. Okay. H equals f over g. So here we're looking at a quotient function, and what we want to find is h prime. So what we're going to do is take this f over g, and we're going to multiply the g across, and we get h times g equals f prime. So now we're taking the derivative of both sides of that equation, and we apply the product rule on the left. So h times g prime equals h prime times g plus h times g prime. Now, we're going to rearrange because we want to solve for h prime. Remember, that's the derivative we're looking for. So we subtract h times g prime. We get h prime times g equals f prime minus h times g prime. And then what do we get here? We get, we divide by g and we get h prime equals f prime over g minus h times g prime over g. And now, what are we going to do? Well, we've got h prime written like this, but we don't want h here. So we replace h with the original function f over g, which is what we defined h as. Now we've got f prime over g minus f times g prime over g squared. And so now all I got to do is just multiply this other guy by g, and now both of these are over g squared, and I can combine my fraction. And I get g times f prime minus f times g prime over g squared. Okay, so with that said, let's go ahead and start writing out some of these problems. Now, when we do these, I think this is really, really crucial as you're first practicing to write out these derivatives fully in terms of the derivative rule before computing any of the individual derivatives. So in this case, we're looking at the product. So this is x squared prime times cosine of x plus x squared times cosine of x prime. That's 2x cosine of x plus x squared times negative sine of x. That's 2x times cosine of x, and I'll just move the negative factor in front, minus x squared sine of x. So there's a couple reasons. First of all, you're much less likely to make mistakes if you write this full expression in terms of the derivatives as you're writing out your product rule. Second of all, if you're turning in a quiz or an exam and it's going to be graded by someone, they're not a mind reader. So if you apply the rule incorrectly versus if you take one of these little derivatives incorrectly, it may be hard for your grader to determine where the mistake was made if you're not writing this explicitly. So that means if you're being graded for partial credit, when you write this rule out explicitly, it lets the grader know, hey, I understood the product rule properly and I applied the product rule properly and I should get credit for that. And then if you make a little mistake on one of your individual derivatives, then you're more likely to lose less points since it'll be clear that your mistake was a smaller mistake rather than the major rule that's being applied. So something to keep in mind. It's a very good habit to make sure you just write out these rules explicitly as you're doing them. Okay, so next we have g of x equals 7x cubed minus 2x over sine of x. So when I take the derivative of this thing, so remember, it was low d high, so the bottom times the derivative of the top. And I'll use Leibniz notation here. Low d high minus high d low. Over low squared. So again, by writing out the rule explicitly without taking any of the smaller derivatives, I'm less likely to make mistakes, and the grader's going to have a better idea of what I'm actually doing and understand where my mistakes were made if it becomes necessary. So now we'll take our derivatives. So the derivative of 7x cubed minus 2x, we've had a bit of practice here, so I'm going to kind of go quickly. This is a constant multiple, 7 times 3x squared, that's the power rule, minus 2 times the derivative of x, which is just 1, minus 7x cubed minus 2x times cosine of x. All over sine of x squared, but we can just rewrite that as sine squared of x. It's the same thing. And now in this case, there's not much else that can be done to simplify this in any meaningful way, but 7 times 3 is 21, so I should at least write that. Okay, that's it for that one. Okay, so now we want to find the derivative of tangent of t, but what we should hopefully recall is that tangent of t is just sine of t divided by cosine of t. So really, I should think of this as taking the derivative of the quotient, sine of t over cosine of t prime. So again, low d high minus high d low over low squared, and I'll just go ahead and skip straight to writing that as cosine squared of t. Okay, so we'll deal with the numerator first. The derivative of sine is cosine. Derivative of cosine is negative sine. So cosine times cosine is cosine squared. Now we have negative sine of t times negative sine of t. The negatives cancel. I get a positive sine squared of t. And this here is the Pythagorean identity. So recall that on the unit circle, we get cosine squared of t plus sine squared of t equals 1. Remember, that's just the Pythagorean theorem on the unit circle, right? When you're on the unit circle, that's the circle with radius 1. So if it's a little bit rusty for you, that means the hypotenuse of your triangle is 1, and cosine is the bottom leg, and sine is the top leg of your triangle. So cosine squared of t plus sine squared of t equals 1 is just the Pythagorean theorem, right? So this is 1 over cosine squared of t, and 1 over cosine of t is secant of t, so 1 over cosine squared is secant squared of t. Okay, so that's the derivative of tangent. Let's go ahead and take a look at another trigonometric function, secant. Well, secant is 1 over cosine of theta. So if I want to take the derivative of 1 over cosine of theta, I can apply my quotient rule again. And we go through the same process, low d high. Minus high d low. Over low squared. The derivative of 1 is 0. The derivative of cosine is negative sine. So these two, so I get 0 here, and then these two negatives cancel, so I get left with sine of theta over cosine squared of theta. And while this is technically the answer, this typically is not how we actually write this derivative. So we have a standard form for this derivative, and we write this form, we rewrite this as sine of theta over cosine of theta times 1 over cosine of theta. That's the same thing. And then sine of theta divided by cosine is tangent of theta, and 1 over cosine is secant of theta. So the way we typically write this derivative for secant of theta is in the form tangent of theta times secant of theta. Okay, so with that out of the way, let's go ahead and look at a little summary of our trigonometric derivatives. So these are going to come up a lot in calculus throughout the entire series. Going to be using trigonometric derivatives all of the time. So you really have to commit these to memory as quickly as possible so that they become automatic. So we already know that our derivative of sine is cosine, and our derivative of cosine is negative sine. And we just saw that our derivative for tangent is secant squared of x. I think part of my table might have got cut off here. Well, let me just fix that. There we go. Okay, so where was I? So we already know the derivatives for sine and cosine. We saw that the derivative of tangent is secant squared. You can also show the same way that the derivative of cotangent of x is negative cosecant squared of x. We saw that the derivative of secant of x is secant of x tangent of x. And you can similarly show that cosecant of x the derivative of cosecant of x equals negative cosecant of x times cotangent of x. So again, we're going to use these derivatives all the time. You're going to want to memorize these so that you don't have to re-derive them from scratch every time you use them. That would be way too time consuming. Okay, so find the derivatives of the following functions. So now we've got some trigonometric functions involved here. So we want the derivative of, with respect to theta, of cosecant of theta over theta squared. Low d high. Minus high d low. Over low squared. Okay, the derivative of cosecant, well, let's remember the derivative of secant is secant x tangent x. The derivative of cosecant looks like the same thing, but negative and using the co-functions. So it's negative cosecant theta cotangent theta. So real quick, to try to reinforce that relationship, the patterns for these derivatives are very similar. It's just the cofunctions end up having negatives in their derivatives. So derivative tangent of x is secant squared. Derivative cotangent is negative cosecant squared. Derivative secant of x is secant x tangent x. Derivative cosecant is negative cosecant of x cotangent of x. So just try to keep that in mind. They're very similar. They just differ by a negative and the fact that they're the cosecant relationships instead of the secant. So now we've got the derivative of theta squared, which is 2 theta. And theta squared squared is theta to the 4th. All right, so let's clean this up just a little bit. I have a common factor of theta that I can pull out, so I'm going to pull out that common factor of theta. And then here, after I've factored out theta, I get left with a negative theta times cosecant of theta times cotangent of theta minus 2 cosecant of theta over theta to the 4th, and theta over theta to the 4th is 1 over theta cubed. So this simplifies to negative theta cosecant of theta times cotangent of theta minus 2 cosecant of theta. Now, generally, you don't have to go crazy with simplifying these types of quotient problems, but if there seems to be some obvious simplification, some fairly easy simplification, you should always do that, because when you get into higher levels, like especially Calculus 2, and you're using derivatives as sub-steps in other problems, then if your derivative work isn't simplified, it can make the work in Calc 2 and later courses more complicated. So you want to do at least any obvious simplification that you see, but you don't have to like go crazy trying to do every little weird trick you can come up with for simplifying expressions. Okay, let's look at another example here. So here we've got g of x, so we want the product of these two things. So the cubed root of x squared times tangent of x, we want the derivative of that. But before I do that, I'm going to rewrite x, the cubed root of x squared, as x to the 2/3 power. Okay, so that's the derivative of the first times the second plus the first times the derivative of the second. All right, and here we just apply the power rule. That's going to be 2/3 x to the negative 1/3 times tangent of theta, or tangent of x, I mean, plus x to the 2/3 times, and the derivative of tangent is secant squared, so derivative of tangent of x is secant squared of x. Now, this would generally be fine, but we can actually clean this one up a lot by doing a couple things here. First of all, we typically will always take negative exponents, move them to the denominator, and write them as positive. It's not a rule per se, but just a standard procedure. So now, maybe I would like to combine my fractions together here. So if I want to do that, I need a denominator of 3 times x to the 1/3 here, which means I need to multiply this by the same thing. And so that actually gives me a nicer numerator expression when I combine these. So in the denominator, I get 3 times the cubed root of x, and up top I get 2 tangent of x plus 3 times, and x to the 1/3 times x to 2/3 is just x, times secant squared of x. So this isn't really necessary. I would have been fine with this first answer. But again, simplifying into something like this might make later work a little bit easier. That just depends on the work you have to do afterwards. Okay, so now we have something a little more complicated in this next example. So here, what we see is we have a product inside of a quotient. So that makes things a bit trickier. So we have to apply both the product rule and the quotient rule. And we have to make sure we understand which to do in which order. So here, we just need to keep in mind that we've got t squared times sine of t over t cubed. So my larger operation here is the quotient. This product is inside one of the quotient functions. It's inside just the numerator. So it's a sub operation inside that numerator. So our outer operation is the quotient. So we need to do the quotient rule first. And let's write it all out really carefully. So again, this is the perfect example of where if you don't write out your rule first, you are very likely to make mistakes on it. So first of all, our denominator is just going to be the denominator squared. And again, it's low d high minus high d low. Okay, so now what do we see? Well, we see that here, t squared times sine of t prime, that's got to apply a product rule. So we're going to write that product rule out inside of the parentheses. T squared prime times sine of t plus t squared times sine of t prime. Didn't give myself quite enough room there. Minus, and here we've got t squared times sine of t times, and the derivative of t cubed is just 3t squared, just the power rule. And in our denominator, t to the cubed, t cubed to the second power is t to the sixth. Okay, so let's go ahead and simplify this further, take a few more derivatives. Now inside this product, we get the derivative of t squared is 2t times sine of t plus t squared times cosine of t minus, and I'm going to put the 3 in front, t squared times t squared is t to the fourth times sine of t. All over t to the sixth. Now we see there's a bunch of multiples of t across the board here. So this is another example where I think it's you really want to simplify this a little bit further. So first let's just distribute. We multiply the t cubed across. We're going to get 2t to the fourth times sine of t plus t to the fifth times cosine of t minus 3t to the fourth sine of t. And so I'd like to be able to cancel some factors with my denominator here. And what I see is the biggest factor of t is t to the fourth up top. So I'll factor out t to the fourth. I get 2 sine of t plus t cosine of t minus 3 sine of t. So t to the fourth over t squared, t to the sixth leaves me t squared on the bottom. And also 2 sine of t minus 3 sine of t leaves me with negative sine of t. Plus t cosine of t. All divided by t squared. So I would say that this is a great example of how the resulting function that you get after a little bit of simplification is a much, much nicer function to work with. So if you're needing to actually use this to evaluate values, you would much rather be working with this function than the one up here. So again, you don't have to go crazy with simplification, but if it's pretty obvious where to go with the simplification, you should go ahead and do it. Okay, so now let's just take a look at this idea in terms of the graphs of some functions. Just kind of focus on conceptually how we relate the graphs of the two functions to applying this rule. So here we've got f times g prime of 1 is what we're asking for, and we're supposed to use the graphs to determine this. So let's first write out our rule explicitly. So this is f prime of 1 times g of 1 plus f of 1 times g prime of 1. All right, and now we just have to look at the information the graph gives us. So when we look at f prime of 1, that's the slope of this line. So what's the slope? It's rise 2 over 1, 2 over 1, which is 2. So I need f prime of 1. I also need f of 1. So what's f of 1? Well, that's just 2. It's just the y value at the point. They happen to be the same. That's coincidence. Now we need g of 1, and g of 1, that's right here. That's 1 1/2, or 3/2. And then g prime of 1, that's the slope at this point. And we're going, the rise is down 1 over 2. So that's negative 1/2. So now we just apply that information into our product rule for derivatives, and we get 2 times 3/2 plus 2 times negative 1/2. This gives us 3 minus 1, which is 2. Okay, so now we're going to look at another example. I'm going to zoom out a little bit just to make this easier. So now we need f over g prime of 5. So again, I'm going to start by writing out my rule. Low at 5 times low d high, the derivative of the high at 5, minus f of 5 times g prime of 5 over g of 5 squared. So here, what do we need? We need to know what g of 5 is, f of 5 is, f prime of 5, and g prime of 5. So we're going to go back. We're going to write all that down just like we did before. Okay, what is f prime of 5? Well, the slope of this line is 0 at 5, so that's just 0. And f of 5 is just 2. That's the y value. G prime of 5 is the slope of this line, so we're going up 1 over 2. So that's up 1 over 2. And the value of g at 5 is 3/2. So just like g of 1. Okay, so let's take a look at this. What do we get? 3/2 times 0 minus 2 times 1/2 divided by 3/2 squared. 3/2 times 0 is 0, minus 2 times 1/2, that's minus 1 over 3/2 squared is 9/4. Multiply by the reciprocal, and we get negative 4/9. Okay, so far so good. We got one more here, f times g prime of 2. So this rule would be f prime of 2 times g of 2 plus f of 2 times g prime of 2. So let's go take a look for this information. So we'll start with f prime of 2. All right, what do we get for f prime of 2? We look at 2. Hey, that's a corner. And hopefully we recall from earlier discussions that that means that this derivative doesn't exist when you have a sharp corner like that. So this does not exist. And if one of the derivatives in this product doesn't exist, then the whole thing does not exist. Okay, well, that's it. Thanks for watching this video on the product and quotient rules.